All right then. So let's call the first poster. Luke, are you ready?
Yes, should work now. So hi everyone. Thank you for having me, and thank you, Abel, for organising everything. So I'm going to talk about voxel printing. Alvaro was just talking a bit about voxels. I'm going to talk about voxel printing in the context of neuroimaging, so MRIs of the brain. So I have a background as a doctor. I work as a medical doctor. And a few years ago, I started working in a field called tissue engineering. So we were just talking a bit about bioprinting. So I worked a bit in bioprinting, and I got very interested in the scaffolds. So typically you make these scaffolds which act as kind of conduits for living cells. And I got very interested in the design of these scaffolds, how you could optimize the structure so that they were somewhat like nature. And that's how I got interested in architecture. So using principles from architecture, things like procedural design and parametric design to kind of automate the design of these scaffolds. And that's sort of how I got interested in voxel printing, because it offered a way to have very, very fine control over the distribution of materials. So this might be very, very simplistic for you guys, but voxels are basically like three-dimensional pixels, so data points regularly spaced in 3D space. And you can obviously encode information at each data point. And it gets very interesting once you transform this into physical materials. So you can have different materials at different points and have very, very fine control over the distribution of those materials. So you can have things like gradients and properties like anisotropy, so different properties in different dimensions, which is much more like natural tissue and natural structures. So I wanted to try and voxel print medical imaging. So people do already 3D print a lot of medical imaging, and it's very useful as a kind of teaching device. It's been used as for surgical simulation, for education, and the kind of typical way of doing it is using what's called segmentation. So it requires you to have some level of like anatomical knowledge. So you have to identify a structure, and then you'd have to go through each slice of imaging, identify the structure, do that throughout the kind of image stack, and then you'd create a 3D model. But obviously you lose the rest of the data. You can over or underestimate the size of the structure. And you can imagine if you're say doing modeling a tumor or something, then an over or underestimation could really, it can make a difference to surgical planning. So voxel printing, or at least converting the medical scans into like bitmap images, would preserve all the kind of fine differentiation you get with medical imaging. And it would hopefully preserve all the dimensions that you get as well. So I chose neuroimaging because it shows very, very fine kind of vasculature, which would demonstrate the benefits of the new process. And it's just a question of how do you convert the MRI data into something that the 3D printer can accept. So this was my process. So you start off obviously with the MRI images. I then used it's an open source software called Simple ITK, which is like a medical imaging software. And really what you want to do is convert the MRI images into the native format for the 3D printer. So basically a stack of images but it's the MRI slices are actually much more far apart than the resolution of the printer. So you have to create a kind of a virtual stack of images and then interpolate between the gaps. So you create these sorts of virtual images, and you stretch them in one dimension because that's just the resolution of the printer. But then you get a very detailed and true to life structure at the end of it. You also have to convert, so scans a grayscale, so pixel values. So you could use multiple different resins. In this case, we just use 2 resins, so transparent and black. But you basically have to what's called dither the image, so convert it to either these black or white pixel values. And for that, I used something called Floyd-Steinberg dithering, which some of you might be familiar with. It's basically just an algorithm which converts these grayscale values into either black or white. But you can use it on color images as well. And so this is a quick video. It just basically shows. So this is like all the bitmap slices just going through. And this is sort of what the 3D printer does. So builds it up in layers. And this is what you're left with. So this is sort of quite a thin slice, but hopefully it shows that you have all this fine vasculature preserved. You can see the differentiation between the gray and the white matter. All the structures are the right size. You can see through it, so it's quite thin, but you can still see an element of like the 3D aspect of it. And so this is another just cross section. So the advantages of this approach over the kind of traditional segmentation approach is that it doesn't require any anatomical knowledge. You can just use these scans, go through this workflow, and you're left with a physical manifestation of the scan. It much more closely mimics natural tissue. So in theory, you could use lots and lots of different materials. You could have soft materials that represent kind of soft tissue, and then harder materials representing bone, which obviously would create kind of physical feedback, haptic feedback on these models, which for planning, surgical simulation, education, things like that, they're much truer to life. And very quickly, I was trying to link this to architecture, but I think you guys obviously have a much deeper understanding of the use of voxels in architecture, but I was thinking about how you can obviously vary the scale of these voxels. So you can have this approach, so using these 3D printers, the voxels are about 10 microns in size, but you could imagine if you change the size of the voxels, you basically change the size of the overall structure, and then the variation, the very tight control of material values and properties and colors across space just gives you an amazing amount of control over the final structure. So there's a couple of references that are very relevant. So Neri Oxman's lab at MIT, they've done some similar work. Those are my contact details. So it's very much still a work in progress. I'm looking at ways that you can use this kind of approach in things like prostheses and what's called orthoses, which are like medical devices that support the body. But yeah, I think it holds great promise in medicine and obviously other fields as well. So thank you very much.